Hi there. Now that we have gone over the relationship between wavelength and frequency of electromagnetic radiation, we're going to introduce how energy fits into that equation, literally. And this picture that you have on your screen right now is a picture of what we call the electromagnetic spectrum. And the electromagnetic spectrum is the range of all the different types of electromagnetic radiation. So electromagnetic radiation is an umbrella term for energy in the form of a wave. But we have actually made other words to be more specific about different subcategories of that. And the only difference between the different types of electromagnetic radiation are the actual wavelength and frequency of the radiation. So you can see on the right-hand side of this diagram that's where radio waves and microwaves and infrared are. And those are longer wavelengths. And then in the middle, you will see that there's the visible spectrum. And that's the only colors, the only wavelengths of electromagnetic radiation that our eyes can pick up. And then on the left-hand side, as the wavelength gets smaller and smaller and smaller, we have ultraviolet and X-rays and then gamma rays. And so one way to think about that and to try and wrap your brains around it is think of, Roy G. Biv. So red is the beginning of that. And the other side of red that we can't see is infrared. Infrared radiation is what is used in remote controls. And when you think of that, it's not harmful. You don't worry about it at all. But then go to the other side of the spectrum, violet. The other side of violet is ultraviolet. And ultraviolet, the wavelength is a little bit shorter, but short enough so now that it is damaging, right? We do worry about ultraviolet radiation. We know that that can cause skin cancer. Right now, we're using ultraviolet radiation because ultraviolet radiation can actually disrupt DNA negatively and cause skin cancer. Or for us, we've actually used that fact, and ultraviolet radiation can be used to disrupt the DNA of viruses like the coronavirus, which is how our goggles get sanitized in between each use. The other interesting thing to note on this picture right here is energy. And so energy is on this diagram, and it shows us that energy increases as you go to the left-hand side. That makes sense. We know that X-rays and ultraviolet rays can be damaging to cells, can cause cancer, whereas everything on the right-hand side is pretty safe. And so now we can quantify the relationship between frequency and energy. And that started with a man named Max Planck. And he discovered that energy can be absorbed or emitted in any fractional amount. And that's sort of weird. When we think about energy being absorbed, we think, sure, energy can be absorbed. I can heat up water and you can see the thermometer go up and up and up. And if you were to stick a thermometer in a cup of water as it was being heated, you would see that it would steadily go up. If you were to zoom in, you would see that it actually doesn't. On an incredibly small level, the amount of energy jumps from here to here. And it's actually a complete jump. And those individual amounts of energy that can be absorbed, that is what he termed a quantum of energy. So energy can be gained or lost in whole number multiples of a specific quantity. And they were like little packets of energy. And yes, these packets of energy he called a quantum. Kind of think of it as the difference between adding sugar or Splenda to a cup of coffee. We sort of look at it like sugar. Like you could add any amount of sugar, a little bit, a lot. But what we've learned is that it's more like Splenda. You add 1 pack, or you add 2 pack, or you add 3 packs. I know there's flaws in that analogy, but you can kind of get the general drift. Okay, so now let's actually do some math here. What is the formula? The formula is that energy is equal to Planck's constant times frequency. Planck's constant is a number, 6.626 times 10 to the negative 34 joules times seconds. That's another number that we will plug into your calculator so that you won't have to keep typing in every time. And we're going to be using this number in the same way that we using this formula, just like we use other formulas. We write the formula, we plug in the numbers that we know, and then we solve using algebra. Question number 1 says, what is the energy of light with a frequency of 1.00 times 10 to the positive 17, 1 over seconds or hertz? So we always rewrite the formula. Energy equals Planck's constant times frequency, and then plug in what we know. We're looking to find energy, right? Circle the do. We circle what the question's asking me to find, which is energy. And this is the number that I know, the frequency. Planck's constant is, of course, a constant, 6.626 times 10 to the negative 34 joules times seconds. And the frequency is 1.00 times 10 to the positive 17, 1 over seconds. I multiply those two numbers together. Look at how the units cancel out. I get seconds in the numerator, cancels out with seconds in the denominator. And then the numbers have 3 and 4 significant figures, so I round my answer to 3 significant figures. So that will be 6.63 times 10 to the negative 17 joules. Joules is the unit that scientists use to measure energy, joules or kilojoules. Let's take a look at question 2. If you want to try and do these problems on your own, you're more than welcome to pause the recording now, do the rest of these problems, and then check your answers. Hey, what is the energy of light with a wavelength of 4.3 times 10 to the negative 7 meters? Again, circle the do, underline the clue. The question is asking for energy, so of course I write the formula for energy. Energy equals Planck's constant times frequency, but I'm not given frequency, I'm given wavelength. So what do I need to do? I need to convert from wavelength to frequency using the formula that we learned in the last video. Speed of light equals wavelength times frequency, 2.998 times 10 to the positive 8 meters per second equals the wavelength, 4.30 times 10 to negative 7 meters times that frequency. Divide both sides by 4.30 times 10 to the negative 7 meters, and I get 6.97 times 10 to the positive 14 inverse seconds as my frequency. Now in my calculator, I'm not rounding at all. I'm going to use that whole number back in my energy formula. Energy equals Planck's constant times frequency, or 6.626 times 10 to the negative 34 joules times seconds, times that frequency, which I just found, 6.97 times 10 to the positive 14 inverse seconds. Multiply those two. Seconds cancel. Again, 3 significant figures because that's the number with the least number of significant figures. And my answer is 4.62 times 10 to the negative 19 joules. The next question doesn't ask for energy, though. It actually asks for frequency. It says, what is the frequency of light? And it gives me the energy. Well, the only formula that I know that has energy in it is the one we've been using. And now I plug in what I know. 3.21 times 10 to the negative 9 joules equals Planck's constant, 6.626 times 10 to the negative 34 joules times seconds times the frequency. Divide both sides by Planck's constant. Round again to just 3 significant figures. and I get 4.84 times 10 to the positive 24 inverse seconds is my frequency. And then last but not least, what is the wavelength of light with an energy of 7.21 times 10 to the negative 20 joules? This question's asking for wavelength. I'm given energy again, which means I can use the same formula. Energy equals Planck's constant times frequency. But this time, when I solve for frequency, I need to then use my speed of light formula in order to convert it back to wavelength, because that's what the question is asking me. So plugging in for my energy, 7.21 times 10 to the negative 20 joules, Planck's constant, 6.626 times 10 to the negative 34, joules times seconds, times frequency. Divide both sides by Planck's constant, and I get 1.088 times 10 to the positive 14, 1 over seconds as my frequency. Again, I'm not worried about rounding because I only round at the very end of the problem, and I'm still in the middle of the problem. Right now I have frequency, but look at what I circled. The question is asking for wavelength. So I take this number. Now I use the other formula. Speed of light equals wavelength times frequency. 2.998 times 10 to the positive 8 meters per second equals wavelength times my frequency, 1.088 times 10 to the positive 14 inverse seconds. Now I divide both sides by that frequency, and I get that my wavelength is equal to 2.76 times 10 to the negative 6 meters. Again, all of these problems on this page had 3 significant figures, so my answer has 3 significant figures.